Here we're taking a look at the two-dimensional truss element. So let's start with a review. We have the truss element stiffness matrix in the element's own coordinate system. So let's go ahead and draw the element. Here's the element's own coordinate system. That little prime there is meant to indicate the elemental coordinate system. And we can go ahead and write out that truss element stiffness matrix as follows. There's our displacements and rotations. We have our stiffness, E times A over L, that's the elastic modulus times cross-sectional area divided by the length. And note that we have some ones here and then a lot of zeros. The ones indicate that we only have stiffness along the axis of the element, and the zeros indicate that there is no transverse stiffness. So here we're assuming 2 dimensions, and we're only looking at the X and Y possible translations. We are not considering rotation in this presentation. All right, so now continuing that review, let's take a look at coordinate transformation. So in coordinate transformation, first we have our global coordinate system, and let's say we have a transformed coordinate system. So the global coordinate system might be, well, X and Y directions we're usually used to, and then maybe the transformed coordinate system, that would correspond to what the element orientation might be. And so we can make a relationship between that transformed coordinate system and the global coordinate system as follows. For example, that U prime would be a combination of U times cosine theta plus V times sine theta. Similarly, V prime would be a combination of minus U times sine theta. Why? Because if you look in this direction, this is actually like that component there is actually going in the opposite direction. And then we go ahead and add V times cosine theta. So those equations are the relationship between our elemental coordinate system and our global coordinate system. And so we can use those to create a matrix form of those equations. Once again, that's our elemental coordinate system, and this is our global coordinate system. And so with that, then we can go ahead and introduce the elemental transformation matrix. So this is our elemental transformation matrix. There's our elemental coordinates, and here are the global coordinates. All right, and they're right here. Maybe we'll come in, you can see that angle theta, which is the angle of this element. And so we can go ahead and write our equation as follows, where we have this as our elemental transformation matrix. This is our displacements for the element in the element's own coordinate system, and this is our displacements for the element in the global coordinate system. So really all we did is we took that transformation matrix from the previous slide and we just applied it both at nodes 1 and node 2, nodes 1 and 2. All right, so now that brings us to our elemental transformation matrix and how it works for both displacements and forces. We can go ahead and write out that same element with the displacements and forces. And so we've seen how it works with the displacements, and the exact same thing is true for forces, where in this equation the transformation matrix itself is exactly the same. We're just kind of writing out the forces, the force vectors in both the elemental coordinates here and the global coordinates there. There's our elemental transformation matrix. One thing we want to emphasize here is that this angle theta must be measured from the first to the second node in the element definition. And so we might see that more when we start doing example problems. But that's very important, because if you don't, it ends up causing a problem later on in the elemental, or probably the solvent process for the finite element problem, finite element analysis problem. Okay, so how can we put it all together? Well, we have our elemental matrix equation in the elemental coordinate system. All right, there we have just ones and zeros there inside that matrix multiplied by the stiffness of the truss bar itself. All right, there's our matrix notation there for the stiffness matrix equation for the element and the element's own coordinate system. And we can relate the elemental and global coordinate system using that transformation matrix for both forces and forces and displacements. And so if that's true, we can now transform our elemental stiffness matrix from the elemental stiffness, or probably the elemental orientation, to the global orientation. And here we go. Here's a butterfly breaking out of a chrysalis here. It's actually kind of nice. We have a butterfly breaking out of a chrysalis right now on our fence. There it is. Takes too long to draw, so we'll just kind of go ahead and zap through that. We have our forces equal to our stiffness matrix equal to our displacements, or multiplied by our displacements. Pardon me, this is the same thing as what we have over here for our elemental matrix equation. And then if we go ahead and apply, or pardon me, make the substitution that we have here, right, for our forces and our displacements using that elemental transformation matrix, we can go ahead and bring that transformation matrix over to the other side using the principle of orthogonality. That will be the transpose once we get to that other side. There we go. And so now we have a relationship between our forces and our displacements in the global coordinate system. This whole section here in the middle, that combination of the stiffness matrix for the element in the element coordinate system and the elemental transformation matrix, that becomes our elemental transformation matrix in the global coordinate system. All right, so we'll go ahead and rewrite that here. And that section right there, that now becomes our global stiffness, or pardon me, our elemental stiffness matrix in the global coordinate system using that elemental transformation matrix. So there's our two-dimensional element there. We're just going to go ahead and write out what each of these terms mean as we multiply everything through. It's common that you'll see this representation here written as follows, where each of the C's represent a cosine, each of the S's represent a sine. That's a very common form. I will personally choose to write it like this because, or pardon me, I don't know if there it is. I will write it like that because that form will work in 3 dimensions. It will work for frame elements, any line element. So I'll use that to be consistent, but for a shortcut, you could also use this form that you have down here. Okay. So that brings us to the reflection questions. And the first reflection question is, how would the stiffness matrix for a spring element in the 2-dimensional global coordinates be written? What would the transformation matrix for the element look like if rotation was also included? In other words, we want to go from our global coordinates to the elemental coordinates. We're including the rotation as well. So what would that look like? And then the next question is, let's say that we wanted to consider an element that would connect nodes 7 and 5 in that order. What would the angle theta be for that element? And so those are the reflection questions for this video on the 2-dimensional truss element.